All right, welcome to the very first introductory lesson on exponential functions. We're going to come back to this and take some additional notes down the road. So this is just going to kind of build that initial foundation. So an exponential function has an algebraic or mathematical form of y equals a times b to the x. And I'm making this a different color so you recognize that this guy up here is your variable. That's what you're going to be plugging numbers into. And A and B are going to be constants, and each one actually indicates something separate. So I'm going to change the color on this just so we kind of see different colors. So A, and then again, that's times B to the x. And we're going to kind of talk about today only what A and B do to this function, and that's it. You'll notice on your notes down here, we have an h and a k, which we've encountered before, and they're going to be very similar. They're going to be shifts, right and left, up and down. And we have a little place to talk about specifically growth and decay, and in those terms, what A and B happen to do in those terms. So I'm going to talk about a few things with A, and this is specifically only when I'm in this kind of generic form where I have no transformations, nothing's being extra is done. I just have an A and a B. And again, those are going to be numbers, but those numbers matter. In particular, A cannot be 0, because that would just make 0. And A, actually, that's the only restriction we're going to put on A. A can be any other number. And so in this form right here, so I'm going to write with no transformations. I have very bad handwriting, and it's even worse with this little guy here, but whatever. With no transformations, because we're going to come back and change this, and this is going to change when we do transform the equation. At this stage right here, if it looks like this, A is your y-intercept. That's pretty exciting news, which means when I put a 0 in, I get out A. And the reason is if I put a 0 up here as an exponent, anything to the 0 power equals 1. So this would just become A times 1, or A. So A is your y-intercept. If A is negative, it's going to do the same thing all of our original power functions did in the beginning of the year. If A is less than 0, if A is negative, it's going to be a reflection. So it's going to do the exact same thing we've talked about before, and you will have encountered that or will be encountering that. And it reflects it over the x-axis. If A is bigger than 1, it acts sort of like a vertical stretch, sort of what we talked about before. And if A is between 0 and 1, I'm kind of running out of room here, so like a half or a quarter, then we have a vertical compression or a vertical shrink. You're not going to see those quite as obviously or visually with an exponential function as you would with some of the other functions that we saw earlier. But basically, the thing to keep in mind is this number out in front acts just like it did in all of our other families of functions, like the a value in quadratics and polynomials. If it's negative, it reflects it down. If it's integer bigger than 1, it's going to stretch it, etc. So this B is what we're going to call our base. It is the base with an exponent up here. B has some other stipulations as well. B cannot be 0. And for an exponential function to truly be a function, B has to be greater than 0. We can't have any negative bases. So we're not going to play around with negative bases. And B does have to be bigger than 0. So that sort of takes care of this piece right here by saying bigger than 0. That doesn't include 0. But B can also not equal 1. It has to be bigger than 0, but it can't equal 1. And that's because if it's 1, I'm just going to get a flat line across at 1. So B is your base. Eventually, it will become help us to recognize what our growth or decay factor is. At this point, if B is bigger than 1, we are going to have what we're going to call growth, which means we're going to shoot up very quickly. And if B is between 0 and 1, so again, a fraction like I was talking about over here, then we have, in essence, what's called decay, which means I'm going to be compressing and coming down. So the curves are very similar because one's shooting up, one is shooting down. This one's increasing always. This one is decreasing always. So those are kind of some of the key features that you're going to get with the exponential function. Now, again, I'm going to skip talking about h and k. We've alluded to growth and decay. This is a very timely exponential curve. This is generally what they look like. I do want to point out, it's a little bit easier to see here, that this right now down here, notice that this thing doesn't come down and cross that. So if I go back to the previous screen, I'm also going to say, in general, unless I do some sort of transformation of this guy, I have a horizontal asymptote at y equals 0. So for this growth graph, it's going to shoot up and get bigger than 0. Here it's going to come down and get closer and closer to 0. And we'll look at those again a little closer in a minute. So that's why this graph comes down here, but this is time spent looking at exponential graphs. So as time went on from January to February to March, the amount of time people have been spent looking at exponential graphs has gone up exponentially. That's supposed to be a funny little joke. Anyway, we're going to do a couple of these, and I'm going to move this out of the way a little bit so that you can see it maybe a little better. There we go. All right, so if I have to graph this, I'm going to be identifying a couple key things. First off, this out here is my A value, is 4. And this 2 is my B value. So what I know from my A value is that it is positive and it is bigger than 1. So when I am looking at graphing this thing, what I know for sure is because it's positive, I'm going to be up here, and if it were negative, I would be reflected down here. So I'm going to be up here. It's positive, so it means I'm going to be stretching it up. B is 2, so that's my base, and basically I'm going to increase my powers of 2 each time I plug in a new value for x. So I think your homework is going to have you try this with plugging in a few points, and so we're going to do that. The first point is, again, there's no transformations, there's nothing being added up here or out here, so I know already from the notes a second ago that if I plug in a 0 in this guy right there, 2 to 0 is 1, so I already know my y-intercept is 4, so I can already put a dot there. There are no transformations on here, so I know my horizontal asymptote is right here at y equals 0, and I'm going to start to build this by putting in a couple more points. I always put in -1 and 1 at this point. So if I put a 1 in, that's the easier one for me because it's just a 1. I would have 4 times 2 to the first, and that's just 4 times 2, so that's 8. So at an x value of 1, my output is now at 8. And if I put in a -1, this is one that's a little tricky. It requires us to remember that a negative exponent means 2 to the -1 is the same as a 1/2. You flip it, and that just equals 2. So at -1, my output is 2. And because I know the general shape of this graph should be shooting up, I can kind of curve this thing. I'm not going to cross that asymptote, and I got to come up through here and get bigger and bigger very, very quickly. There we go. That's my first graph. Now I'm going to erase some of this, so if you need to look at it, you can go back and check it out. I'm going to erase it because I need it for my next graph. There it goes, gone, gone, gone. And I'm back to writing, and I'm going to make a new table to fill in over here for my x and y axis. Now over here, notice that my A value is -4. That means this purple graph I graphed over here is going to be reflected, and it's going to be reflected down here. That's what that negative out in front has done for us all year. My B value is 1/2. So notice that's very different than a 2. So 2 gets bigger and bigger and bigger. So a half is that graph that gets smaller and smaller and smaller. So there's two things going to be happening. This, if there were no negative here, this graph would kind of compress, but the negative is going to flip it over. And again, no matter what I'm talking about here, I've got no transformation. So if I were to start by putting a 0 in right here, anything to the 0 is 1. So my initial y-intercept would be at -4. There's no transformations happening here, so I know I have a horizontal asymptote right here. It's the worst horizontal asymptote I've ever drawn at y = 0. And now I'm just going to pick some other points, and I'm going to try -1 and 1. And again, I'm going to do 1 first because that's easier for me. So if I put -4 times 1/2 to the first power, that's just -4 times a half. So that equals -2. So at 1, I'm at -2. So there's that point, and I've already got that point in there. And now if I plug in -1, this one's a little bit trickier. I get -4 times 1/2 to the -1. Now remember that negative exponent just flips this, so this becomes -4 times 2. It doesn't change the sign of it, it just flips it. So 1/2 to the negative first becomes 2, and that equals -8. So at -1, I've got to come all the way down here to -8. And again, I remember the general shape is this general shape's happening. It's just depending on which direction it's going. And so here I've got to come through it and level off at my asymptote. So don't forget to level off at your asymptote. So it kind of is this one, but it's compression and it's flipped over to the bottom. So I hope that kind of gives you a little quick synopsis and guide on how to do the homework and what's going on with these brand new exponential functions. But basically, because my exponent is a variable, as I put more numbers in there, the exponents are going to drive that base, either make it bigger and bigger and bigger, or if it's a fraction in there, it's going to make it smaller and smaller and smaller. So there you go. Enjoy.